In this lecture series, we're going to be talking about atomic and periodic table properties and the trends therein. After watching this video series, students will be able to identify the various trends on the periodic table, as well as explain the physical causes of these observed trends. So before we can really talk about periodic trends, we actually need to understand how the particles, the subatomic particles, protons and electrons, interact with one another within an atom. And what we need to understand is something called Coulomb's law. Coulomb's law states that the magnitude of the electrostatic force of attraction or repulsion between charges is going to be directly proportional to the product of the magnitude of the charges and inversely proportional to the distance between them. Okay, so what we're going to do is we're going to look at this equation here. This force of attraction is going to be directly proportional to the magnitude of the charges. Okay, so Q1 and Q2 each represent one of the two charges, and the r squared here represents the distance between the charges. Okay, so let's go ahead and let's look at how this equation is represented physically within some examples. Okay, so if we go ahead and we look at these 2 point charges, I want you to notice that one is positive and one is negative. Just like you guys learned in grade school when you played with magnets, opposites attract. So we know that this type of interaction here is going to be an attraction as opposed to a repulsion if these were the same. Okay, so if we look at this example here, we have a positive 1 charge and a minus 1 charge and a specific distance here. Now, if we were to compare the attractive force between these two charges versus the attractive force between these two, we would have a different value. Okay, and the reason why is because if we go and we inspect the charges here, notice here we have a 2 plus charge here and a minus 1 charge there. So in this case, the 2 plus and the minus 1 is going to be greater overall charges than the plus 1 and the minus 1. Okay, and since our attractive force is going to be directly proportional to the product of those two charges, we know that the force of attraction for this example is going to be greater than this example. Okay, now in addition to the actual magnitude of the charges, we also have obviously distance being a component that contributes to our overall attractions or repulsions. So if we go ahead and we look at this example here, once again, we have a positive and a negative charge, so it's going to be repulsive forces. In this case, we have the same magnitude of charges with a positive 1 and a negative 1, but what the difference is here is that the distance between them has increased. Okay, so what you're going to notice here is that the larger distance here is going to mean that our denominator here is going to be much larger. A larger denominator is going to mean that when you divide in that value, it's going to decrease the overall force. So the greater the distance between two charges, the weaker the attractive or repulsive forces. So in this situation, the charges are going to be in closer proximity and therefore are going to be stronger than in this example. Now, because we have positively charged protons and negatively charged electrons within an atom, these type of Coulombic interactions are going to be things that dictate some of the features that we see for ionization energies and electronegativities and things that we'll discuss later on. So effective nuclear charge is basically the pull or the charge from the nucleus that's experienced by an electron in a mini electron atom. So something besides, say, hydrogen. So electrons in mini electron atoms are basically being attracted to the nucleus. The nucleus is pulling them in. You have a positive charge inside the nucleus, and obviously electrons are negatively charged. But simultaneously, they're also being repelled by the other electrons. And the process of those repulsions are known as screening or shielding. Now, these repulsions basically would be very, very difficult to calculate in terms of individual effect because obviously each electron is positioned in a different location throughout the atom. So instead of calculating each individual repulsive force that's created, we actually just look at all of the contributing electrons as an average environment. So
basically that shielding or that screening that's occurring is basically an average environment. It's an assumed or calculated average environment. Now, Z effective is smaller than your actual nuclear charge because of the fact that Z effective accounts for the repulsions that we discussed up here. So basically, if we had a single electron on the outside and no electrons in between the nucleus and that electron, we would be looking at an unencumbered interaction between that nucleus and that electron that was being pulled in or attracted to that nucleus. Now, Z effective is calculated by the equation you see here. So we take that nuclear charge, which is represented by the number of protons, so basically how many protons you have in that specific atom, minus basically the number, approximate number of core electrons. We'll talk about that here in a second, but basically this equation will allow you to get a pretty general effective nuclear charge for each individual atom. So how would we calculate the effective nuclear charge for sodium? Basically, we know that sodium has 11 protons because its atomic number is 11. We know that it has one valence electron, so the number of electrons and protons needs to be equal in a neutral element. So we know that 10 of those electrons are core electrons, so that's why we have our S value as 10. We subtract these two, and our effective nuclear charge is therefore +1 for sodium. Now, your S value, or basically that environment created by those electrons, can actually be affected by something called orbital penetration. So basically we've talked about probabilities of where electrons are going to reside, and we've talked about them with respect to these orbital distribution diagrams. And if you look at these, notice, for instance, the 2s, okay, in the 2s orbitals, there's a very high probability of the electrons being, this distance from the nucleus. However, there's a small probability that they could be closer. Same thing goes for 3s and so on. So in this case, the 3s orbital, the 3s electron that we're looking at here, the one that's actually being affected by that nuclear charge, actually has, a few chances of being or residing closer to the nucleus. So basically what ends up happening is your S value ends up decreasing because the reality of it is that the shielding that we're assuming is based on all of the electrons that are doing that shielding basically maintaining a specific distance from the nucleus. However, because there is some penetration effects, so basically there is a chance that that 3s electron would be closer to the nucleus, that shielding that we see when we just assume that they're all residing in a specific location at all times becomes altered. So that S value gets a little bit smaller, and subsequently your positively charged protons in the nucleus are able to be more effective. So effective nuclear charge trends in terms of going from left to right on the periodic table, you're going to see an increase in your Z effective. Okay, so it's going to be getting larger. And this is due to the ineffective screening by electrons in the same energy level. So basically, if we look at something like lithium and beryllium, so if we go from left to right in this situation, what I want you to notice is that obviously the number of protons for both lithium and beryllium are different. So when we plug in our Z values, our number of protons, those should be different values. Now, based on the calculations that we've seen, our S value is determined by your core electrons. Lithium and beryllium both have the same number of core electrons, so the shielding that is being done is basically equivalent. So when we end up doing our Z effective calculation, that shows that our beryllium is going to have a stronger pull on its electrons that are on that outer shell. So we would expect some trends to correspond to this type of pull. So what we need to understand here is that the core electrons are going to be the ones that are doing the shielding. Any type of screening or shielding by electrons that are being added into the same energy level. So I'm talking about continuing to add electrons into this 2s orbital, as we see with lithium and beryllium. Those additional electrons don't actually affect the Z effective, at least not in a very large way. Okay, now remember, we are calculating based on assumptions, based on an average environment. However, the calculations that are done compared to more complicated calculations are actually pretty close. Now, Z effective, when we're going from top to bottom, so basically going from the top of our periodic table all the way down, are going to slightly increase from top to bottom. And this is partially due to a more diffuse core electron cloud. So basically, as you continue away from the nucleus, the electrons are having to, cover more distance or more area in terms of that atom's structure. So the electron density isn't as tight. And so the effective nuclear charge is going to be stronger. So even though, based on our calculation equation, we would expect something like lithium and sodium, when we compare those, so we'd expect them to have exactly the same nuclear charge, they actually end up having a pretty different set. And that's because, that sodium atom is going to be larger. The electrons floating around are not going to be able to block that nuclear charge from the nucleus as well, because basically they're spread out over a larger area. So atom and ion size are basically calculated from bonded materials. So the bonding atomic radius is half of the nucleus to nucleus distance of identical atomic radii. So if we're just looking at atom size, we're getting that by measuring basically half of the nucleus to nucleus distance. So half of this distance here is going to give us our radius for each of our atom, and they have to be of the same atom type. And so when we're calculating that, we're using it from bonded molecules. Now the trend for your atom size and also your ion size is that it decreases from left to right. So basically, as you go from left to right, you're getting smaller. Okay, and as you go from top to bottom, you're getting larger. Okay, so knowing the trend is important, knowing what to expect. You should be able to, look at two atoms that are adjacent to each other and indicate the size of that atom and how they compare to one another. And you can use these trends. However, you also need to be able to explain why. And before we go ahead and continue in talking about why, take a look at this nice little diagram. It's a good visual representation of the size differentials. Obviously, every chart is going to have been measured a little bit differently, so different charts may look slightly different. However, you can see the general trend as you go from left to right. They're getting smaller, and top to bottom, they're getting larger. Okay, so we'll talk about the reason why here in a minute. Okay, so why are they getting larger? Why are the atomic radii getting larger as you go down the periodic table? Okay, well, the reality of it is as you go down the table, you added a bunch of electrons, and you've added them into different orbital layers with different principal quantum numbers. So basically, as you add more layers, as you have a larger principal quantum number, the probability of electrons residing farther from the nucleus increases. So you have a higher chance of having an electron farther away from the nucleus. So you subsequently are getting a larger atom. Shielding also starts to come into effect. Those core electrons are going to block that interaction or that attraction between the nucleus and the valence electrons. So they're not going to be held quite as tightly. Now, when we're going from left to right, why is that the case? Okay, well, as we saw with our Z effective, our effective nuclear charge is increasing from left to right because the same set of core electrons is doing the shielding of the nucleus. But as you go from left to right, you're increasing the number of protons that you have inside that nucleus. So basically you have the same shielding from left to right, but at the same time you're adding more pull from the nucleus left to right. So basically what ends up happening is you have an ineffective shielding process, and as you go from left to right, you keep adding more and more protons, so those pull tighter and tighter on that electron that you're looking at, and basically you have a decrease in size from left to right. So top to bottom, the main contributing factor is basically the probability of having electrons farther away from the nucleus as you get a larger principal quantum number. So, and from left to right, that effective nuclear charge is the bigger feature that is contributing to the size change from left to right. So once again, probability distributions and then your principal quantum number. These are the things that are contributing to the increase in size from top to bottom. And your Z effective is going to be the biggest contributor for the change in your size from left to right. Basically, that nuclear charge is able to be more effective as you're being blocked by the exact same layer of electrons going from left to right on the periodic table. So here we have a table of radii for all the different atoms. If I gave you a table like this, I may ask you to compare bond lengths of different molecules. And basically, if I ask you to do that, basically, remember the size, right, or the bond distance that occurs between two atoms is basically going to be the sum of the two radii. So element A and element B, if I know the radius of B and I know the radius of A, I can find out the bond distance between the two, or at least an approximate calculation, by summing the two. So bond length is going to equal A plus B, the radii of each of those. So if I ask you something like this, like to predict the bond length in each one of these molecules, I would look up on the chart the radii for phosphorus and bromine, as well as arsenic and chlorine, and basically sum those as you see here. So your phosphorus and bromine radii get summed. This gives you a value of 2.20. Same thing for your arsenic and chlorine bonds, or radii, excuse me. You sum them together. And what we can see here is from this calculation, the PBr bonds are going to be slightly longer than the arsenic chlorine bonds. So take some time to get familiar with some of the general atomic radii here. You can see the trends. Just kind of get comfortable with the changes from left to right and top to bottom. Just kind of an approximate value. I'm not expecting you to memorize this table, but just be familiar with it as well. Make sure that you're familiar with utilizing something like this to calculate your bond lengths. Also, angstroms here. It's a unit of length or distance. We use it all the time when we're talking about bond lengths and things of that sort. So just be familiar with that as well. So looking now more specifically at the ionic radii, or the ionic radius, we need to talk about what happens when a neutral atom forms an anion or a cation. So if we look at our pictures here, I want you to notice that I have a sodium atom. Sodium atom is a metal. Typically, they give up electrons. So if sodium loses an electron, it's still going to have the same number of protons, right? Because number of protons is what determines if it's a sodium atom or a sodium ion. So 11 protons is going to remain constant throughout this process. However, when ionization occurs, when sodium loses that electron, instead of having 11 electrons to pull on, okay, or to interact with, it now only has 10 because it's basically lost that one. So now these 11 protons are pulling on only 10 electrons. Because of that, you see a size difference between your neutral atom and your ion. So basically, the nuclear charge, the effective nuclear charge, is going to be greater in the sodium ion because there are less electrons and the same number of protons. So those protons are going to pull more tightly. So when you lose an electron to form a cation, the cation that you form is going to be smaller than the parent atom being the sodium atom. Now, anions, obviously, are just the reverse of this process. In this case, we're looking at a chlorine atom. Chlorine atoms have 17 protons, 17 electrons. If I pick up an electron to form a chloride ion, I still have the same number of protons. I have 17 protons, but now I have 18 electrons to contend with. So the effective nuclear charge in this case is going to be diminished. Those protons are going to now have to hold on to an extra electron. So the size of the anion is going to increase with respect to the parent atom. So cations are going to decrease in size when compared to the parent atom, and anions are going to increase when compared to their parent atom. So the ionic radius, or this size, is basically calculated from the radii of anions and cations that are found within crystalline ionic compounds. It's figured out in a very, very similar way to what we indicated with the atomic radii. But obviously it's not done with the same type of element. So it's not a iron or nitrogen bond that we're looking at. In this case, we're actually looking at lithium and fluorine crystal structure, and so we're looking at those ionic radii from those substances. So if we look at the trends that we see, the ions kind of follow the same trend as the atomic radii. From left to right, we do see a slight decrease. At least we do for the first row and second row elements. However, what I want you to notice is that when we break between the cations and the anions, okay, when we go from one side to the other, I want you to notice that obviously there's going to be a size increase on the anion side, right? We just talked about why that's the case. So although the trend is true for the halves, so the cation side and the anion forming side, it's not necessarily true all the way across the table. Okay, I hope you see that. From top to bottom, we do see an increase in size. The anions and cations both get larger as you go from top to bottom. So they generally follow the same trend as the atomic radii that we just discussed. However, you got to pay attention to this break in the cation side and the anion side. So if we go ahead and look at an example where a question could be a given, basically here what they've asked you to do is to predict the trend in the radius for the following ions. So we have beryllium +2, magnesium +2, calcium +2, and strontium +2. Beryllium, magnesium, calcium, strontium, these are all in that alkaline earth metal group. They all normally form a +2 charge. As you go from top to bottom, though, we know that the typical trend is what? We know that it is going to increase in size top to bottom, whether you're talking about atomic radii or you're talking about ionic radii. So because they're all in the same group, okay, the trend is very straightforward. So basically the trend you should expect is that as you go from top to bottom, so as you go from beryllium to magnesium to calcium to strontium, they should be getting larger. Okay. Now, each of these ions, when discussed with respect to their original neutral parent atoms, would be described as smaller, right? Okay, because remember, when you remove electrons, you get that contraction because the nucleus is pulling more tightly on less electrons. Okay, so if you are comparing the neutral versus the ion In this case, the cations are going to be smaller than the parent atoms. However, in this case, they're just asking you to predict the trend for just the ions, and as you go from top to bottom, you're getting larger. So in this case, that would be your answer for this respective question. Okay, so the last example we looked at, we were comparing ions that were all in the same group, in this group 2A here. However, there could be questions where they ask us to compare ions that are not in the same group. And in this case, we're being asked to compare a isoelectronic series. So
what we mean by that is that the group of ions or elements all have the same number of electrons. So oxygen normally has 8 electrons, but the oxide ion has a 2- charge, meaning 2 electrons have been obtained or gained. So there are 10 total electrons. Fluorine normally has 9 electrons, but the fluoride ion has 10 electrons. Sodium normally has 11 electrons, but it has a +1 charge, so it means electrons have been removed. Okay, and so on and so forth. Each of these examples here have 10 total electrons. Now, every single one of these ions has the same number of electrons. However, what is different is that they all have a different number of protons. Okay, and that's going to affect the relative size comparison that we do for this series. Okay, so if we go ahead and we write out the number of protons in each of these ions, we can then analyze them from the perspective of attractive forces. So if all of them have the same number of valence, or same number of total electrons, the number of protons is going to directly impact the overall attractive forces. So the elements that have more protons are going to have more Z effective, and a bigger Z effective is going to mean a smaller atomic radius or ionic radius. And so what we end up with here is the following ranking for these particular ions. And this is what leads us to the ability to compare isoelectronic ions or atoms in a series.
Ionization energies are the energy that's required in order to remove an electron from a gaseous atom. So basically, we just talked about ions. In this case, we would be referring to cations, the formation of cations, because we're removing electrons. So ionization energy here is basically the energy required to remove that electron. Now, there's different types of ionization energy. Now, the highest energy electron, so the one that's farthest away from the nucleus, is going to be the one that's removed first. So, the first ionization energy, or IE1 or I1, there's different types of notations. First ionization energy is the energy required to remove the first electron. So in any element that you're looking at, the electron that's farthest away from the nucleus is going to be the one that's removed first, and the energy required to do that is going to be your first ionization energy. Second ionization energy is going to be the second electron that's removed from that atom. The third ionization energy is the energy required to remove the third electron from that atom, etc. So remember, as I mentioned, the ionization energy is referring to the removal of electrons. So in that situation, we are going from neutral atoms to cations, basically the loss of electrons. So the energy that I have to put in to remove electrons from this neutral atom, each successive electron removal is known as the ionization energy. And each value is going to be different depending on which electron is being removed. Okay, so the trends for your first ionization energy is that it increases from left to right, generally speaking, and decreases from top to bottom. So, as I said earlier, you need to know the trends. However, we are going to discuss the why that is associated with the trends, and that's the more important feature. So you do need to know the trends. You need to be able to discern things with your periodic table based on your understanding and your memorization of the trends. However, you also need to be able to explain the trends. Okay, so why is the trend left to right generally going to increase? Why is that first ionization energy going to increase? The reason why is because as we go from left to right, we have more and more protons being added to that atom, or to each atom. So the number of protons increases from left to right. as we increase those number of protons, the electrons that are also being added into a shell that does not really contribute much to the shielding of the nuclear charge. So your effective nuclear charge is going to pull on those electrons and hold them more tightly, so it's going to be more difficult to remove that electron. So removing that electron being more difficult means that we have to put more in. So the ionization energy that we have to put in is going to be greater. So your left to right increase is due to that effective nuclear charge. As you go down the group, it gets easier to remove electrons. And why is that? That's primarily because the electrons are farther away. Remember, those electrons have a higher probability of being farther from the nucleus because you're increasing that principal quantum number. They're therefore less able to be held onto by the nucleus. That effective nuclear charge is not quite as strong. So the probability of being farther away is greater. And you subsequently end up with electrons that are just much more easily removed because the nucleus is not able to hold on to them as tightly. So why is this trend closer or the opposite of what we see with the atomic radius? Well, the smaller your atom is, the more strongly the nucleus is pulling on those electrons. So the stronger that attraction, the harder it is to remove the electrons that are in that specific atom. And basically there are little jumps that we see inside each group, and basically that has to do with electron configurations and things of that sort that don't really want to lose electrons. We've talked about half-filled, completely filled shells, etc. We'll talk about more details about ionization energy here though. Here's a fairly decent ionization energy value chart. We have several different numbers here. Obviously these values are ionization energies. Notice there is that general trend from left to right. There are slight differences, and that has primarily to do with things like half shell being half filled, like we see here. For nitrogen, we have one electron in each of the p orbitals here, so basically we have a half-filled shell. When we add an additional electron, basically the electrons have to pair up in one of those p orbitals, and that basically causes a slight instability in the atom, and basically makes it where that electron's slightly easier to be removed. We see another jump here in the completely filled shell examples, these noble gases. They have a completely full shell, and so the stability afforded to that type of configuration makes it where removing electrons from there is going to be energetically unfavorable. So we talked about the jumps in energy that we see as we're going from left to right on that table. We talked about initial removal and basically the progression throughout. One of the things that was emphasized in the last slide was talking about that jump between that between the partially filled and the completely filled shell. So basically those core electrons, right? So if I look at magnesium, magnesium wants to lose 2 electrons to be like the nearest noble gas. There is stability in having the electron configuration of a noble gas. Now, we see a large jump between the ionization values when I remove a 3rd electron from a magnesium ion. So if initially they want to give up their electrons, they're fine with doing that. However, when we start trying to remove core electrons, the stability that's afforded makes it where it's very energetically unfavorable to remove that electron. So we have to put a lot of energy in to disturb those core electrons. In the case of aluminum, aluminum wants to give up its 3 electrons in order to have the noble gas electron configuration. But once again, when we remove an electron from that core, from that stable, completely filled shell, we see a very large jump in that energy. So half-filled, completely filled shells, those are going to basically contribute to these jumps that you see. However, the biggest difference is going to be due to the disturbance of those octet setups, so basically those noble gas electron configurations. So if we were to look at the aluminum example, and we were to talk about the trend that we see, aluminum is going to want to give up 3 of its electrons in order to be like its nearest noble gas. So it wants to form this 3+ ion. So these first 3 ionization energies are basically the removal of those electrons, those first 3 electrons. And we expect that to become more difficult as you move through the removal of each electron, because as you remove electrons, the proton number stays the same. So as I remove one electron, the electrons that remain are held more tightly by the nucleus. Okay, so we expect these three to increase as we go through the removal progression. Okay, so this is normal. We expect this because of the fact that the protons pull on remaining electrons. Okay, so this is logical. Okay, now this huge jump that we see here when we go to remove that fourth electron, that is being caused because we are trying to remove core electrons. Okay, so remember, the first three electrons that are being removed, aluminum wants to do this. It wants to gain its electron configuration that is similar to or the same as its nearest noble gas. This is what all of the elements are doing in terms of reactivity. Now, when we go to remove those core electrons, we're disturbing the stability of having that full shell. So that's why this fourth electron has such a large jump and a large gap from the third. So if we look at this example, we're looking at phosphorus and sulfur. Phosphorus and sulfur and their first ionization energy, so the removal of their first electron. So normally we would expect sulfur to have a slightly higher first ionization energy than phosphorus. And the reason we would expect that is because sulfur is smaller. It has a more effective nuclear charge. It has the nucleus that's pulling more tightly than phosphorus. However, we notice that phosphorus actually has the higher first ionization energy. And this has to do with having that half-filled shell setup. Okay, so basically, both of them have a completely filled 3s orbital, right? We're going to ignore the core electrons for this example. And then their 3p's are where we're going to actually see a difference. Okay, so if we look at phosphorus, phosphorus has 1, 2, 3 electrons in its p orbital, so they're all hanging out in their individual seats. When we look at the 3s, okay, it has an additional electron. It has 4 electrons in its p orbital, right? Because of the fact that it has a pair of electrons that are sharing a seat, the repulsion that occurs here causes this element to not be quite as stable as this one with the half-filled shell. So it's easier to remove this electron than this one because basically this other electron that is sitting in the same seat is trying to kick this one out. Okay, so the ionization energy here for your sulfur, your first ionization energy, is going to be basically slightly lower than your phosphorus. And that's because there's stability in having a half-filled shell versus an unevenly or unequally filled shell. So electron affinity is referring to basically the production of anions. So the going from a neutral atom, such as, let's see, a fluoride atom, a fluorine atom, to a fluoride ion. So basically picking up an electron to give you an anion is what we're looking at here. So basically the reverse of ionization energy. So electron affinity refers to the change in energy that occurs when an electron is picked up by an atom. And a lot of times this process of gaining an electron basically releases energy. This release of energy is why we represent our electron affinity values with negative values when available, right? So the more negative that value is, the easier the addition of that electron. So basically, energy is released. It's what the atom wants to do. So basically, as we go from left to right on the periodic table, we're typically going to increase our electron affinity. Lots of or more energy should be released as we acquire an electron. And top to bottom, it's going to decrease in that same sense. Now, if we think about it from left to right with respect to the effective nuclear charge. That electron really wants, or that atom really wants that electron because it can handle an additional electron. That nucleus is desiring or able to hold on to the electron that is being added. And the stability that's afforded the atom by gaining that electron, such as something like fluorine becoming a fluoride ion, is beneficial to the atom overall. Top to bottom, electron affinity is not going to be as great. It's not going to want, the atom is not going to want to pick up electrons because you keep adding electrons to layers that are further and further from the nucleus. The nucleus is not able to hold on as tightly to the electron, so the desire to pick up additional electrons is lowered. Although electron affinity and electronegativity have the same trends, they're actually different, basically, things. Okay, so electron affinity is the measure of the energy released when an electron is picked up by a neutral atom. Okay, electronegativity can apply to basically any substance. An electron doesn't actually have to be passed along or picked up. There is no necessity of having electrons exchanged. Okay, so electronegativity measures the ability of an atom in a chemical compound, so basically something that's bonded, to attract electrons. There's no transfer, there's no energy released type of thing. We're talking about the sharing of electrons inside molecules. So if we look at something like this, right, so we look at the electrons and how they're being shared between the carbon and fluorine atoms in this bonding set here. Okay, so please make sure you're differentiating between electronegativity and electron affinity. Now, the trends for electronegativity is left to right, you're increasing. Okay, so the closer you get to fluorine, the higher your electronegativity, because fluorine is the most electronegative element. Remember, it's very small. It has lots of protons. It really wants to be like its nearest noble gas. Top to bottom, your electronegativity is going to be decreasing. Remember, there's more layers, they're bigger atoms. The nucleus is not able to pull on the outer electrons quite as well. The desire of that atom to pick up additional electron, or sorry, that desire of that atom to hold on to electrons or pull electron density towards it is definitely diminished. Okay, here's a little chart with electronegativity values. Noticed going from left to right, we are getting closer to fluorine. Our electronegativity values are increasing, and pretty much the same thing is true going from top to bottom. We're going to see a decrease in electronegativity values. They don't really want to have electron density towards them or pulled towards them. So remember, electronegativity is different than electron affinity. Electronegativity refers to basically the distribution of electrons in bonded structures. Electron affinity is actually the picking up of an electron to form an anion.